So I'm going to share the presentation. I don't know if you can see the full screen right now.
Yes.
Okay. So first of all, thank you very much for the presentation and also for the invitation to participate in this forum. For me, it's a great pleasure to be here. Uh, my talk is going to be focused in the role that ionic liquids may play and play actually in analytical sample preparation. This is a very wide and very broad topic, so I will focus the attention especially on the developments that we have designed in our laboratories in the last years. So considering that the forum or the conference is multidisciplinary, I think that this is a good way to start my talk. Yes, presenting the importance of sample preparation in analytical chemistry. Um, when we want to analyze a sample, okay, in our laboratories, we usually face two main limitations, two main shortcomings. The first one is related to the low concentration of the target analytes in our samples. Um, so these analytes are usually at a concentration below the instrumental detection limit. So if we, for example, inject directly the sample, we are not going to detect the analytes even when they are present. And the second shortcoming is the complexity of the matrices. Obviously, this is not the best example because this is a glass of water. But if you are working in bioanalysis, for example, with urine, blood, or whatever, if you are doing, for example, food analysis, even environmental analysis, you can find very complex matrices. These matrices contain a lot of compounds that may interfere with the determination of our targets. So in short, we have some sensitivity and selectivity issues in our daily basis. So sample preparation in general and extraction techniques, in particular, try to solve these problems by a somewhat selective isolation of the target compound from the sample matrix. So we usually talk about enrichment of the analytes because we increase the concentration of the analytes in the final extracts, and we use as well the term cleanup because the final extracts are cleaner than the original samples. So these are the main objectives. So the performance of all these procedures, all these sample treatments depends on the materials that we are using. So it depends on the type of solvent, if we are working in the solid phase extraction context, or the type of solvents, if we are talking about liquid extraction techniques. And interestingly, the ionic liquids may participate in both processes, because I will explain how can we use, for example, ionic liquids as solvents, but also as solvents if we immobilize them in an appropriate support. So the second thing is interesting because we are in the green chemistry era, so we are aware of the impact of our activities have in the environment. Um, we know that the chemistry, our discipline, have a double role in this field. On the one side, chemistry is a source of pollution. We have to accept that, but on the other side, chemistry is the solution to this pollution because we can, for example, develop remediation processes to reduce the pollution. We can monitor, for example, the presence of pollutants in the case of analytical chemistry in different environmental compartments. So we know that. In the analytical chemistry context, the definition of the green analytical chemistry principles can be considered a milestone of this evolution. In fact, you can find the definition of these principles in this article, okay? And you can find as well a QR code here in this part of the slide. So this is a link to the, for example, to the article that I'm describing in this slide. You will find this QR along the presentation. So the green analytical chemistry considers that sample preparation is a step that has a potential environmental impact because we are using solvents, we are using, for example, energy. We have to apply energy in some stages of the sample preparation, and we are generating some wastes. So the first principle of the green analytical chemistry states that direct analytical techniques should be applied to avoid sample treatment. So I'm saying at the same time that I am a scientist. I think that I am environmental responsible. So I'm aware of the impact of our activities, but at the same time, I'm saying that the sample treatment, which is my field, can be considered a risky step in this scenario. So this may sound weird, but it's not weird at all. If we, for example, read the wide analytical chemistry concept, this is a very, very recent concept. In fact, you can find here the article in which these principles have been very recently defined. And here is the QR code for the link to this article. And the wide analytical chemistry concept defines three main dimensions. The first one is the green dimension. Okay, this is related to the ecological aspects. For example, the toxicity of the reagents, the amount of reagents that we are using in our procedures, the wastes that we are generating, and so on. The second dimension is the red dimension, which is related to the analytical aspects. For example, the scope of application, the sensitivity of our techniques, the precision, the accuracy, so they are very important or relevant analytical features. And the last one is the blue dimension, which are related to the productive considerations, like, for example, the costs associated to our analytical methods, the time required for doing the measurement. For example, the number of samples that we can analyze per hour is the usual parameter that we use in this context, and other requirements. So the wide analytical chemistry, and the term is comes from the red, green, blue code that is used for the definition of colors. The wide analytical chemistry use all these dimensions to define or to evaluate an analytical methodology. So the question that we can make is it sample preparation accepted under the wide analytical chemistry umbrella? And the answer is very simple. It's a resounding yes. So we have to keep it in mind that the main aim of analytical chemistry is to obtain information about chemical systems. Okay, so this is our main objective. So if we need an analytical sample preparation step to get these results, we can apply this analytical sample preparation technique. Okay, we can make an effort making greener the approach, but we can apply this sample preparation technique because it is needed to obtain useful results from the system under study. So, for example, the use of ionic liquids can be considered in this context because in some cases, especially when we are substituting organic solvents, conventional organic solvents by ionic liquids, we are doing the things greener. Okay, then we can discuss the toxicity and so on. I'm not an expert on that, but it is something that we can discuss. So ionic liquids can be considered in this under this green analytical chemistry realm. So the main aim of this slide is just to present a general overview of the work that we have developed in our labs related to the use of ionic liquids in sample preparation. So we started in 2008 using ionic liquids in the microliquid liquid extraction context. Then we move in 2013 to the...
Rafael,
Yes?
I'm sorry to interrupt you, but some of our researchers say that they don't hear very well. So I don't know if it's the audio, like the microphone is not close enough, or
I'm going... Let's check. Okay, I'm going to change my... Now it's better? It's better now?
We will ask the audience if they
yes.
can hear hear well. Please, someone.
Dr. Mario says it looks better.
Okay.
Okay.
Okay, so I have changed the phones. So probably this was the problem. So if there is any problem, just tell me and I will try another option.
Okay. Thank you very much.
Okay. So I was just presenting here the different approaches that we have developed in our lab according to the use of ionic liquids in the sample preparation context. So we started in 2008 in the microliquid liquid extraction field. We moved in 2013 to the microsolid phase extraction context. And in the last years, since 2016, we have been working specifically in the use of magnetic ionic liquids and magnetic polymeric ionic liquids. And the last approach is the immobilization of these polymeric ionic liquids into paper. This is a way of design new sortive materials. Okay, so in fact we are working on this project currently. So just as a brief summary, because in the next slides I'm going to share with you our experience, especially focusing the attention on the different properties of ionic liquids that we have explored. Okay, so in the microliquid liquid extraction, we have checked different techniques: the single drop microextraction technique, the dynamic microliquid liquid extraction, the dispersive liquid-to-liquid microextraction, and the in situ, which is usually called in situ solvent formation, dispersive liquid-liquid microextraction. So, as a brief summary, let's check our developments in single drop microextraction. So, this is a very simple strategy. This is probably the first technique in the liquid phase microextraction context, and it is very simple because it consists on using a small drop of a solvent as an extractant phase. It provides high enrichment factors, and you can develop the technique in three main extraction workflows that are defined in the slide. In the direct immersion mode, we immerse the drop into the sample directly. So the solvent and the aqueous sample is in close contact. It is used for the extraction of non-volatile compounds, especially. In the second workflow, it is the so-called headspace single drop microextraction. We locate the drop in the gaseous phase above the sample here. So this extraction technique is especially indicated for semi-volatile or volatile compounds. And finally, the three phases mode, which is not pretty common, but you can apply as well. In this case, you are playing with the ionization state of the analyte. So you have to work with a pH gradient between an aqueous drop and the sample. And here is a layer of organic solvent, which is an interface between both aqueous phases. So the main problem of using, for example, conventional organic solvents in single drop microextraction is the evaporation of the solvent. Okay, for example, if you are using chloroform as a solvent, so if you develop the headspace technique for a long time, you are going to lose completely the solvent. So you don't have any solvent to analyze at the end of the process. So if you substitute this organic solvent by an ionic liquid, you can, for example, extract your sample for longer times, okay? Just increasing, in this case, the pre-concentration factors. So this is an advantage, obviously, but there is a problem. If we are using a non-volatile solvents like an ionic liquid, we cannot analyze directly this liquid by GC, gas chromatography, because this is not compatible at all. So in this case, we developed a special interface. I'm not going to explain the interface. We can discuss if you want, but this is not the aim of the slide. Yes, we describe a special interface just to make the ionic liquid compatible with the gas chromatograph. So, for example, compare here the chromatograms obtained injecting directly the ionic liquid into the chromatograph. So the chromatogram is not clean. There are a lot of peaks here. You can see here the analytes, but you cannot see other compounds, and there is obviously here a matrix component from the ionic liquid. And this is the chromatogram obtained using the interface. So it's cleaner, and you can identify clearly the analytes. So using this interface, we have analyzed, for example, monoaromatic compounds in water. You can see here the analytes. This is especially interesting because this is benzene that cannot be detected if you are using an organic solvent for the headspace single drop microextraction, because the organic solvent will give you here a huge peak that overlap with the signal of the analyte. And here, this is another approach for the determination of 3-allomethanes in water using ion mobility spectroscopy. This is a portable device, so we can do, if it's required, the analysis on site. So the second type of technique that we developed was the dynamic microliquid liquid extraction. This is a extraction technique that we proposed for the first time. We exploit here the high viscosity of the ionic liquids and the higher density compared with water. So the extraction device is a Pasteur pipette. Here we aspirate a small volume of ionic liquid, and then we can aspirate the sample, and the sample pass through this plug of ionic liquid during the mass transference. Okay, at the end of the process, we can recover this ionic liquid for instrumental analysis. So the process is very simple. We automated it using just a syringe pump, and we apply that for the analysis of drugs in urine very easily. And you can see here a chromatogram, yes, a characteristic chromatogram for this application. In the third approach, in the microliquid liquid extraction, and I'm going just to present ideas, not the application or data or whatever, because it depends if you are interested in the application or not. But this is just ideas that you can apply in other analytical problems. We design a special workflow to use ionic liquids in the dispersive liquid-liquid microextraction context. This is an in-syringe device that we propose for the first time. The process is very simple. We take a volume of sample using the syringe, then we injected a mixture of ionic liquid and an appropriate solvent inside the sample, creating a cloudy solution just formed by tiny drops of extractant. So if you are doing that, if you are doing a good dispersion, you are increasing the extraction kinetics. Okay, so you are doing the extraction faster. And finally, for doing the phases separation, we need just to move the plunger of the syringe, and we can recover the ionic liquid in the lower connector of the syringe. This is the only application that we have reported with this technique, but we are very proud of it because it has been used by other researchers for doing automated dispersive liquid-liquid microextraction using automated syringe. So we are proud the impact of this research. And the last thing that we have done in the liquid-liquid extraction, and we will comment this reaction later, is the in situ solvent formation. In this case, we exploit the metathesis reaction. So we know that the solubility of the ionic liquids in water can be modified just selecting the counter anion. For example, if you are using an imidazolium ionic liquid and you are using acetate as counter ion, this ionic liquid is soluble in water. But if you substitute this acetate by hexafluorophosphate, you can transform this soluble ionic liquid in a very hydrophobic ionic liquid, creating a biphasic system. So the idea of this approach was playing with this tunable solubility. The idea is to add the soluble ionic liquid to the aqueous sample, so creating an homogeneous media, and then we can add an hexafluorophosphate, for example, potassium hexafluorophosphate solution to this media in order to induce the metathesis reaction to create the hydrophobic ionic liquid that can be recovered or can be collected from the sample containing the analytes. We designed a special interface for doing the analysis. Okay, so sorry for that, the names are in Spanish, but I can explain easily. The idea is to introduce the ionic liquid containing the target analytes in a vial. We can close the vial. This is a cap containing a septum. And then we introduce here a needle. There is another needle here. And we use an helium stream that comes with this path, pass through the vial, and drives the analytes to the GC injection port. In this case, in order to promote the desorption of the analytes from the ionic liquid, we can increase the temperature of this ionic liquid just to promote this transference to the GC port. In this case, it is essential as well the non-volatility of the ionic liquid, because in this case we are not going to get any signal from the solvent in our chromatograms. And here you can see, for example, 2 chromatograms obtained for analysis of chlorophenols at different concentration levels. Okay, so it is possible to do this approach very easily. Very briefly, the first developments in macro solid phase extraction. We designed 2 types of materials, the ionic liquid coated silica and the ionic liquid coated magnetic nanoparticles. The coating process is very or pretty similar in both approaches. So in our first approach, we are starting from silica particles, and we modify the surface of these silica particles with chlorosilanes. And then if you add, for example, N-methyl imidazole, you can you can covalent immobilize an imidazolium ring in the surface of the particle. That's simple. We are very happy with this first work because we demonstrated, and as far as I know, this was the first time that it was demonstrated that the metathesis reaction can work as well with solids. So if we take, for example, the silica modified with ionic liquid in the surface, and we disperse this silica into water, we can stand alone this tube for 10 minutes, and you can see here that the particles remain in the dispersion. But if we add the hexafluorophosphate, we can induce not the precipitation, but we break the dispersion easily. If the same procedure is applied to non-modified silica, the behavior is completely different. Okay, we are not doing anything here. We are not breaking the dispersion as a consequence of the addition of the counter ion. So we apply that in homogeneous extraction in a similar way that the previous work in the liquid phase macroextraction context, and the phases, in this case the solid and the liquid, can be easily separated. And finally, in this in this section of the presentation, our works with magnetic nanoparticles covered with, first of all, with silica and then modified with ionic liquids. The process of the modifications are similar to the previously described. The beauty of this type of materials is that we can, for example, disperse them easily into the sample, and we can recover them easily using an external magnet. So we don't need any centrifugation step. We don't need any filtration to recover the solid after the application. Okay, so there are a lot of applications of this type of magnetic ionic liquids, even in catalysis for the degradation of polymers. So I think that they have a lot of potential. And just for the last part of the presentation, we are going just to discuss a couple of works in more detail. We have been working with polymeric ionic liquids in the last years. Probably you have been working with this type of materials. There are a lot of type of reactions that you can use to synthesize these type of polymers, especially because we don't have a strong organic background. We have selected a very simple approach, which is not exploited at all in the analytical chemistry context, which is the so-called Radiaszewski reaction. This is a very simple process that takes place in water. So you don't need, for example, a specific solvent for synthesizing the ionic liquid, and you can use mild conditions. Okay, so the synthesis can be developed at room temperature in 24 hours, or if you want to increase the kinetics, you can heat the solution at 60 degrees or 80 degrees, and you can obtain the polymeric ionic liquid in just 1 hour. So the process is very simple. The Radiaszewski reaction uses a diamine. We are usually commonly the hexamethylene diamine. Okay, so we have here 2 molecules of this diamine. We are using glyoxal, we are using formaldehyde, and an acid, in our case, acetic acid. So if you mix all these reagents just with water, you can create this polymer, okay? And look at that, the counter ion comes from the acid that you are using during the synthesis. In our case, it's commonly acetate. Okay, if you prepare these polymeric ionic liquids and then you evaporate, you are using, for example, here we apply a vacuum evaporation. We can purify this ionic liquid to obtain a liquid like this one. Okay, so this is a viscous liquid that we can use for different purposes. We have done I think, a very complete work on characterizing this type of polymers, because this was the first time that we were working with them. We use the matrix assisted laser desorption ionization coupled to high resolution mass spectrometry for doing an analysis of the polymer. You can see here the spectrum that we obtain, and here the structure of the ions that we can measure in the gaseous phase. Okay, this is not the substance that we have in the solution. This is the ion that we are creating when the laser is focused into the sample. So we have observed that the acetate takes a proton from the imidazolium ring, creating a carbene, and this is the type of ions that we are observing. This is the polymerization degree that varies between 3 and 11, so the chains are not too large. Anyway, we are working just to know if the problem of not observing larger units are due to the technique that we are using. Okay, but this is a thing that we are working on it right now. We check that we can apply the metathesis reaction with this type of polymers. So if we take, for example, the polymer in the acetate form, which is soluble in water, and we add hexafluorophosphate, we can create a biphasic system. it's not as easy as, for example, occurs with the monomeric or normal ionic liquids, but you can do it. And then if you take this polymeric ionic liquid into the hexafluorophosphate form, and you, for example, analyze the polymer by MALDI as well, you can observe this spectrum, and these are the ions that we are observing in the gaseous phase, which are different to this one. In fact, the spectrum is different as well. Okay. Just for the confirmation of the structure of these polymeric ionic liquids, we use the proton nuclear magnetic resonance. So for doing this, or for applying this technique, is very, very important to do this purification process, because if you analyze the bulk polymeric ionic liquid into the acetate form, you are going to observe peaks coming from the polymer, but also peaks coming from all the reagents that you have used for the synthesis. So at the end, the spectrum, sorry, is very complicated to reanalyze. But if you do this purification process and you analyze the polymeric ionic liquid into the hexafluorophosphate form, you observe here, you can obtain a very simple spectrum. We have assigned here the different hydrogens in the structure. So you can see here the hydrogens, and here the hydrogens present in the spectrum. And very, very interesting, if you make a zoom of this zone, okay, you can observe a tiny peak corresponding to acetate. That means that the metathesis reaction can be used to purify the ionic liquid in a large extent, because the acetate that is observed here is a very, very small signal compared with the rest of the signal coming from the polymer. So this is interesting, at least it is interesting for us. What are the type of materials that we have prepared with this Radiaszewski reaction? We have synthesized magnetic polymeric ionic liquids. So you can see here the structure of the polymeric ionic liquid, and here you can see the different structures that can be created if we use magnetic nanoparticles covered with amine groups as reagent. Okay, so theoretically, a magnetic nanoparticle covered with amine groups is a polyamine. So it may, how to say, you can use it as reagent into the Radiaszewski reaction, okay? Because you have an amine there that can participate on the synthesis of the polymer. The main problem of this procedure is that the architectures that you obtain are not easy to be described, because, for example, you can obtain this type of material, which is a magnetic nanoparticle covered with a polymeric ionic liquid chain, but this option is also possible, which is a polymeric ionic liquid acting as a bridge between two magnetic nanoparticles. Okay? From an analytical point of view, this is not a problem, because at the end we are obtaining a solid with a good sorption capacity. And here you can see some microscopy pictures. This is the picture coming from the magnetic nanoparticle silica, coated with amine groups. So the particles are somewhat dispersed. But if you analyze the magnetic nanoparticles covered with amine groups that have been participating into the Radiaszewski reaction, you can see here a higher aggregation as a consequence probably of this type of structures that can be formed as a consequence of the reaction. We have used this type of materials for the extraction of acidic drugs in several samples, and you can also apply this type of materials for the extraction of tellurium species, also in water. Both articles have been developed in collaboration with the University of Cuyo in Argentina. So these are the main type of materials using the magnetic polymeric ionic liquids. Just to finish with this presentation, I'm going just to give yes, a brief explanation about one of our hot topics in our laboratory, which is the use of paper as support for the synthesis of sorted phases. So the main aspects or the main interesting aspect related to paper are this one. It is a sustainable support. So if we are, for example, worried about the impact of our activities in the environment, one of the decisions that we can take is using natural materials for creating new sorted phases. So paper is a natural material, it's cellulose fibers. Okay. It is very cheap and affordable, so you can find paper everywhere. In fact, we are using filtered paper for doing our materials. You can use as well chromatographic paper, but filtered paper gives good performance to the final materials, and it is affordable. This is one of the objectives of our group, doing things that are simple and affordable for all the scientific community. You can use this paper modified with sorted phases in thin film microextraction, and obviously it is easy to transfer between laboratories. So we are collaborating with some groups, and you can prepare, for example, the paper-based sorted phases, and you can send these materials by postal mail. So it is very simple to send to other laboratories. This is a work that we developed with Professor Carla. I think she's attending, Carla Toledo. She's attending to the webinar. So we developed this work with her. So the idea was just to immobilize the polymeric ionic liquid into paper. And for doing that, we check different approaches. One of them is to introduce, for example, amine groups into the paper surface using a silane. We didn't obtain good results with this approach, but theoretically it can be possible. Okay, but we didn't obtain results or good results because the distribution of this polymer was not homogeneous. We use as well polyvinyl chloride as a support into the paper to introduce this polymeric ionic liquid. In the same way, we didn't obtain good results or good coverage of the polymeric ionic liquid into the paper. And the last approach that we used was a combination of the deep coating technique and a thermal curing. The idea is just to introduce the paper into the solution containing the polymeric ionic liquid, and then we dry and we heat this paper at a high temperature, 120 degrees, for 30 minutes, just to make possible the interaction between the amine groups from the polymeric ionic liquid and some carbonyl groups that can be found in cellulose. So the paper usually contain 2 or 3% of carbonyl groups in the surface, which are imperfection of the paper, but we can exploit that just for doing the immobilization. The thermal treatment does not affect the structure of the polymeric ionic liquid, because you can see here the Maltitov spectrum for pure polymeric ionic liquid and the same polymeric ionic liquid treated at high temperature. So the spectra are comparable, so there is no degradation of the material. And just the last slide. So you can find here a microscopy picture of the surface of the paper. We did some elemental analysis in the surface. You can see here the phosphorus and fluorine atoms coming from the counter ion, and we use as well fluorescence measurement just to detect the presence of polymeric ionic liquid into the paper structure, because this polymer has some native fluorescence. So in the raw material, no fluorescence is detectable, and here when the paper is modified with polymeric ionic liquid, you can see some signals coming from the polymer. Just as a brief conclusion, so ionic liquids are very versatile solvents, you know that, but especially in the analytical sample preparation context, due to the different properties that we have discussed. We can, for example, modify the solubility and dispersibility of this type of materials playing with the counter ion. That's interesting. This is a suggestion, so you can use the Radziszewski reaction, which is very simple to synthesize polymeric ionic liquids with different functionalities. We are working on that currently. And if you introduce these polymeric ionic liquids into the cellulose substrates, you can do, for example, interesting application in analytical chemistry, for sure, but also in environmental science, for example, for the remediation processes by sorption, but you can do as well some catalysis, because there are a lot of works using this type of materials as catalytic materials just for destroy pollutants or whatever. Just finally, the acknowledgement to the group. You can find here the logo of our group, which is the Affordable and Sustainable Sample Preparation Research Group. You can find here as well our Twitter account, my Twitter account, and the Twitter account of the boss of the group. And obviously, thank you very much for the funding and the support for all the organization, the Spanish government, the Instituto, our Institute of Nanochemistry, and our university. And finally, and this is pretty important, thank you very much, gracias, obrigado, for your attention.
Thank you very much, Professor Rafael, for this wonderful presentation. Now we have room for questions. You can raise your hand and you can make the question directly to Professor Rafael Lucena, or you can write down the question on the chat so we can read it for Professor Lucena. Elsie, there is Professor Boyan Iliev.
Hi, this is Boyan Iliev from Ionic. I have a question actually on your slide on polyionic liquids and their absorption onto paper. I believe it was numbered with 8. If you could go back to that, please, for a second.
Okay. Let's check. I want to share the.
Yep, that's one. No.
This one?
Yep.
Okay.
That's the one.
Mm-hmm.
I mean, you show here that when you use the, let's say, aminoimidazole, you get a reaction on the imidazole, but actually the primary amino group should be more nucleophilic, don't you think? I mean, have you actually any proof that that's exactly the way it's reacting? I mean, not that it actually really matters probably for the application, but.
So according to the, for example, to the literature, you can, sorry, yes. According to the literature, you can use this type of imidazole to introduce by a nucleophilic attack into the polymeric chloride this structure. So we check if using this molecule, we can develop the same reaction, okay? Just to introduce these amine groups in the surface and use them to participate into the Radziszewski reaction. But unfortunately, we didn't get the results, especially because we observed that the polyvinyl chloride, which was coating the paper, was lost during the reaction, so it was not possible for doing that. So we don't have this, for example, we did some, or we tried to do some infrared spectra, but we didn't obtain the proper results here.
Okay, thank you very much.
I have a question on the chat. It says 2 actually. First, how do you inject the ionic liquids in the analytical equipment that you show? And the second one on your technique for dispersive LPME, what can you tell us about the kinetics? So the first one is about how do you inject the ionic liquids in the analytical equipment?
Yes, I'm going to go. This is the device. So this is the device that we use. So this is how to say interface that we design using Swagelog elements. So it is very simple to design. We have here a cotton piece, okay, and we have here a carrier gas, and here we have also a septum. So after doing the single drop microextraction technique, we take our ionic liquid and we inject our ionic liquid here in the cotton piece, and here the helium used as carrier gas, pass in this direction and take the analytes to the injector of the gas chromatograph. But the ionic liquid is not injected in this injector, which is a very high temperature. So we are using here a temperature around 140 degrees. So it is not very high to destroy or degrade the ionic liquid, and the ionic liquid remains here. Obviously, you can do just a limited number of injections using this interface. So you can do 10 injections, and then you have to remove the device and introduce a new one. Because if you increase the volume of ionic liquid here, you can inject that finally the ionic liquid into the system. Okay, so you can use this device for doing several injections, and then you have to change this interface by a new one using a new cotton piece here. Okay, this is related to the process of the injection of the ionic liquids into the gas chromatograph. Related to the, I think that the question was related to this one, this procedure, liquid microextraction, and the kinetics of this procedure.
Yes.
Yes.
Yes. Okay. So the process is very rapid. So we have observed that if we study, for example, how the signal increases with the extraction time, we observe that 1 minute is enough to achieve the highest signal. Okay, so we are assuming that we are reaching the partitioning equilibrium with this type of devices just in 1 minute. Okay, because we are increasing the superficial area of the ionic liquid, creating a lot of tiny drops. So we are increasing the surface, and therefore we are obtaining the rapid transference of the compounds from the bulk sample to this ionic liquid in just a couple of minutes. So a very fast process.
Thank you for your answer. So I have one more question. How much ionic liquid you can recover after this process?
With this one, yes.
Yes.
The main problem is that probably you can observe here that we are injecting 280 microliters, and finally we are recovering around between 30 or 60 microliters depending on the condition. So we are not recovering all the ionic liquid. From the analytical point of view, this is not a problem. If we are recovering always the same, this is not a problem, but we are not recovering all the ionic liquid for sure.
Okay. Thank you.
Thank you very much. More questions? Remember that you can write down your question in the chat so we can read it. I have a question in the meantime. Very interesting presentation, especially the alternatives you have presented for the microextraction technique. I wonder if you have looked into thermodynamics of this process.
When we are talking, for example, in the microextraction context, we use to study this thermodynamic, but in a indirect way, because we for example optimize extraction time. This is our way of how to say to study the kinetics and the thermodynamic at the same time, because we try to obtain the maximum signal in the as quicker as possible. Okay, but we are not doing some theoretical studies about the partitioning of if we are very close to the equilibrium or not. I can say that if you compare, for example, all these approaches, for example, we are far from the equilibrium in single drop microextraction, and we assume that because if we want to obtain or we want to reach or achieve the equilibrium, we need a very large extraction time, and this is not how to say practical, because in this case you need 2 hours for each sample. So we need results from our samples, but as quicker as possible. And we are very close to the transference or the thermodynamic here in the dispersive and also in the in situ solvent formation. And when we are working with the dynamic, probably this is an intermediate situation. Okay, so we are not very far from the equilibrium, but we are not working at the equilibrium at all.
Thank you. Any other question? Okay. If we don't have more questions, well, I would like to say thank you very much, Professor Rafael Lucena, for your nice and very interesting presentation. I hope this webinar can help to develop a more multidisciplinary background for all the researchers presented here. And also, I would like to thank the audience for the attendance.